Hello, and welcome to the unit on linear momentum and collisions. We're going to start by defining a new quantity, and that is linear momentum. It's a lowercase p with a vector over it because it is a vector. It will have direction. And by definition, this is mass times velocity. So we're encountering another one of those instances where we have a vector times a scalar giving us another vector. So keep in mind that when this happens, the direction on the velocity will be identical to the direction on the momentum. You'll need that to solve some of our problems. I can write the change in momentum, just like we do change in everything, the final minus the initial, being mindful that these are vectors. And this is called change in momentum. It also goes by another name. It's called impulse. So if you're working a problem and it asks for the impulse, what it's really asking for is the change in momentum. All right, let's look at a problem an equation that involves impulse. If I take the impulse and divide by the time frame, that gives me the net force when we're dealing with a change in momentum. So this would be the net force to increase the momentum or decrease the momentum. I can multiply both sides of this equation by time, and I have another way to calculate the change in momentum. So another way besides final minus initial. We can take the net force on the object times time to get the impulse or the change in momentum. All right, so there is a little experiment we can do to think about this equation conceptually. Let's suppose I had 2 raw eggs. So those are my 2 raw eggs, and I'm gonna hold them up really high above the floor, and I'm gonna get equal amounts of paper towels to put on the floor.
The one on the left has the paper towels laid flat. The one on the right has the paper towels all scrunched up into like a little nest. Maybe we even run some tape around it to keep it all together.
Same amount of paper towels. If I drop, or when I drop, both of these raw eggs, they are going to be released from rest, so 0 velocity. They have potential energy, we'll remember from a previous chapter, and they're gonna have the same amount of potential energy. And as they fall, they lose potential, they gain kinetic. Right before collision, they'll have the same speed. Right before collision, identical speed. Now, the collision is talking about a very small time frame. It's talking about the moment that that eggshell touches something to the time it quits moving. So both eggs are going about the same speed right before the collision. And right after the collision, what's the speed of the egg? After it's done colliding with the floor or the nest, it's gonna have a 0 velocity. So the change in momentum of both eggs has to be identical. Now, what's different between these two, what'll happen is this one will break and make a mess, and this one gets cushioned and doesn't break. And the reason for that is it has a greater time frame to slow down. This one has a bigger time frame to slow down, therefore it experiences a lower net force. This one has a very small time frame to slow down, so it's going to have a bigger force on the shell. All right, so let's look at our second conservation thing in physics. We've already had conservation of mechanical energy. Now we are encountering conservation of linear momentum. The linear momentum total of your system has to remain constant. So total, if we have more than one object, we're going to do quite a few problems where we'll have two objects. We can sum up all of the momentum initial. That has to equal the momentum final. And this is another way I could expand this out. So the initial momentum for object 1 plus the initial momentum for object 2 equaling the final momentum for both objects 1 and 2. In this course, we're going to look at two different kinds of collisions. And I have a little demo here that shows the two kinds of collisions. And I have them behind me on the board here, elastic and inelastic. If I have two balls, pretty similar mass, same size, I'm going to take these two balls and drop them. You want me to do it again? This ball bounces back up. It makes a collision with the table that's fairly elastic. This one just goes thud. It's like dropping a lump of clay. It has a collision with the table that we call inelastic. In a collision that is elastic, we have two things conserved. We have momentum conserved. We also have kinetic energy conserved. This is different than the energy conservation that we had before. Before we talked about mechanical energy being conserved, and so that would be our kinetic plus potential. This is just kinetic energy being conserved. So when the ball that bounced went down after the collision, it had the same amount of kinetic energy. It was just going in a different direction now. The ball that was kind of like a lump of clay that just splatted had momentum conserved before and after the collision, but kinetic energy is not conserved. If you're working a problem and it ever has two things stick together, so someone jumping in the air and catching a ball and moving afterwards, that's a kind of stick together. If you had two cars that were coming into an intersection and they collided and locked bumpers and moved off in one direction together, that is another version of stick together. And those are always going to be inelastic collisions. So for this situation, I have to have momentum conserved and kinetic energy conserved. So this is momentum being conserved. And this over, so I've expanded it out here. So this is momentum conserved for two objects, initial and final. And this is kinetic energy conserved. I could do a lot of algebra, and feel free to ask for us to do this in class if you want, but you can also find it on the internet or take my word for it. There's a lot of algebra solving these two equations simultaneously. What we end up with is this equation. And I go out of my way to really note this is for the elastic situation because I have both momentum and kinetic energy conserved. Lots of algebra gets you to this equation. This is only used for collisions that are elastic. So it's on your equation sheet because it is helpful. It is a huge shortcut in terms of the number of algebra steps you have to do if you're trying to satisfy these simultaneously. So you can use this one, but not for inelastic problems. Okay, now we're gonna go into two dimensions. So we're gonna think about glancing collisions or collisions that occur in 2 dimensions, 2D. So I have a sketch here of, say, I'm looking at a drone view. I'm looking down on a green ball that is moving completely along the positive X direction, and there's an orange ball that's a little bit in the way, but not completely. And so it's going to hit and glance off, and when it does that, The green is going to go that way, and the orange is going to go that way, and now I am in 2 dimensions. Recall momentum is a vector. So what that means is I'm going to write my equation for momentum conservation in the x direction and in the y direction, because it has to be conserved in the x direction. Momentum has to be conserved in both the x and the y directions. Now I know there's a lot of scripts on here. If I expand this out, this is the momentum of object 1 in the x direction initial. Well, in this example, if this is object 1 and that's object 2, the initial momentum of this one is 0 because it's still. So often that'll happen in these problems. You'll have some of the terms are 0. And so this is the momentum in the x direction final, and the momentum for object 1 and the momentum for object 2 in the x direction final. So we'll use these to solve some problems involving collisions in 2 dimensions. Great, so I think you have a couple of concept quizzes to do that should help deepen your understanding of linear momentum and collisions.